Guys, so this video, let's talk about group action and some of its consequences. Okay, so this is my group theory PowerPoint. I built my file myself, and you can go to. I will leave the link for other videos, basically related to group theory. Okay, so in this video, let's talk about group action, and after we prove a talk about group action, then we can talk about the zeros theory. Okay, so the group action, that means that by the way, please subscribe to my channel. Okay, so you have a group action, you have a group action on a set, act on set, give a set. So basically, you're giving a group G and an element S, which will give you another element in S. Satisfy when identity act on S will be S and GHS will be GHS. So yeah, this is transit, and this is called a left G action. Okay. So one idea in the group, very important idea is that if you give an S in S and you let G to permute S, this is called orbit. Okay, and also a stabilizer of GS means that if you give S, you ask all the group collect all the group elements such that GS equals to S, called a stabilizer of S. Okay, so theorem is that GS is a subgroup of G. Okay, so this is trivial because identity fix belongs GS because our assumption, and also alpha, when alpha and beta belongs to GS, it's very easy to see alpha beta belongs to GS. Okay, because alpha beta GS, alpha beta S means that alpha S, right, which is S. So alpha beta belongs to GS, and also if alpha belongs to GS, then alpha inverse belongs to GS because alpha S equals S, right? So alpha inverse alpha S, well, it can be written as alpha inverse S, right? But this is identity from these rules, so must be S. Okay, so famous theorem that I will not prove here. But it's very trivial. Means that so GS is a subgroup, right? But not indeed a normal. So G quotient GS will be as a left coset, right? So this coset will be isomorphic to theta S. At least their number will be the same. And the proving idea is that you map the left hand side GGS to GS. Okay. Okay, so the second theorem that which is really important, this is basically called class equation. So we will use this to prove very interesting fact. Okay, so theorem 2 say that the number of S as a set will be sum of the orbit, right? So it's like so different orbits, right? Different orbits will separate S. So S can be written as a distinct union of the orbit. Okay, so in order to prove this, all we need to know is that we want to prove that there's no intersection of each orbit. So this means that if orbit 1, orbit in S1, orbit in S2, they have some non-trivial intersection called S bar, then they will be exactly the same orbit. So this means that any two orbit will not intersect non-trivially. And the reason is that let's say GS1 equals to HS2, right? Then the H inverse GS1 will be S2. So S2 will be orbit of S1, right? So if S2 be the orbit of S1, then the whole orbit of S2 will fall into S1, right? And there will be the same. Okay, so now we can talk about the class equation and center. And I built some other videos about center. I will post in the link below. Basically, I proved some. I think in other video I proved some basic rules of center. Like one famous example is that if G mod ZG is abelian, then ZG is cyclic. Or is cyclic ZG is abelian. Yeah, sorry. Okay, so the special case is that I use G act on G itself, and I define GH to be GH G inverse, and this is obviously the group action. Okay, because the identity G, what G is identity fix H, right? And in this example, that 1 has its own orbit, right? Because 1, when H equals to 1, right, every 1 gives to 1. So the orbit of the identity element will be identity itself. And the stabilizer, that's called ZG, basically is for all the element H such that they commute with G. Okay, so from class equation means this equation, right? So the left-hand side will be group G, the number of the order of the group, and plus 1, right? 1 is identity, and all the other representative when G equals to 1, non equals to 1, and G divided by ZG, right? Because this guy is this guy, right? So yeah, so this is the famous class equation. Okay, and then we define a total center, or basically usually you as ZG, or just for some simplicity, sometimes I usually write Z. So it's all the elements such that HG equals GH for H belongs to G, and obviously this is a normal subgroup of G. Okay, so there's a theorem that we will use in the combined zero theorem. We will prove that order 60 is the non-abelian, is the smallest non-abelian simple group. So theorem says that if your group G has the prime of the power, right, P is prime, then you have non-trivial center. So order of prime power group has a non-trivial center. And the proof is really simple, right? Because we know that Pn, right, by the class equation is 1 plus the G divided by all the representative, which is non-identity, right? But G is Pk, right? Is by P power, that's a Pn. So the idea, so if none of ZG is Pn, right, the right hand side will be multiple of P, and the left hand side is multiple of P, right? So if you have two multiple of P minor, their difference is 1, which is leads to contradiction. So at least one of ZG must be whole group, right? But if some of ZG is whole group, then that means that this G will belongs to the center. But this G is non-trivial, right? Not 1. So you have non-trivial center. So the center must be non-trivial. Okay. Okay. This is very strange theorem that which will prove this the following theorem. So the order of prime square group is abelian, right? So the theorem says that if G is P square, which breeds prime, then G must be abelian. Okay, and so the proof that is very easy, right? We know that the center is non-trivial, but G is P square, right? So center is also normal subgroup, so also subgroup. So there are two cases: Z is P or Z is P square. If Z is P square, then that means everything commute with everything, right? So Z will be the total center will be the group G. So we have that, right? Otherwise, that if Z is P, let's take some G which is not in the center, then let me investigate ZG, right? But you see, if Z is order P, then ZG is a non-trivial larger group, right? Cover Z because Z is commute with everything, right? ZG only care about the element which commute with G. So ZG is greater than Z, but Z is P, right? And G is P squared. So the possibility is that ZG must be P squared, right? But G is P squared, so ZG will be the whole group, right? So this will give you ZG be the whole group, but this will implies that everything in the group commute with G, so G belongs to Z, which is contradiction to our assumption. Okay, so Z must be P squared, so that means that G must be abelian. Okay, yeah, so this is this video, and you can go to my other videos. Basically, the next topic is Zeno's theorem, and I used a very easy group action and only used 20 minutes, and I proved that 3-0 theorem. So in the next videos that we will prove this famous result that 1 by 1. I think none of the YouTube videos they do this. Okay, so I do 1 by 1. I will go 1 to 60 and prove that 1, 2, 3, 4 up to 59. None of them are simple. None of them are abelian and non-abelian and simple, right? So we will prove it. Okay, and I will see you guys in the next videos. Yeah, that's it.